Hello class. Today I thought we would pick up where we left off on pH. So today we're going to discuss how we use pH and continue on with some techniques like titration and making buffer solutions. This is really important if you're in the allied health field. You will be making buffer solutions, or at least you'll be working with buffer solutions. And you need to understand how a buffer works. But in order to understand how a buffer works, we generally have to talk about titration. And before we can talk about both of those, let's just review the pH scale. So the pH scale, we said, is the pH stands for negative log of the hydrogen ion concentration, or also called the hydronium ion concentration. And I like this slide here because it shows that here we have a very small amount of the hydroxide ion concentration, 1 times 10 to the negative 14th molar, which means that the hydrogen ion concentration has to be 10 to the 0 molar. And the reason why that's the case is that the ion product constant of water, which is 1.0 times 10 to the negative 14th, equals the concentration of the hydronium ion, or we'll just say hydrogen ion for short, times the hydroxide ion concentrations. So when we multiply these two concentrations, it must always equal 1 times 10 to the negative 14th for pure water at 25 degrees Celsius. So you see, as the hydroxide ion concentration decreases or increases, the hydrogen ion concentration has to decrease. So we go from 10 to the 0, 10 to the negative 1, which is a tenth, 100th, 1000th, 10,000. Now we're down to 100,000th. The other thing I think it's really important here is that, let's say you're drinking distilled water and it's a pH of 7, and let's say you like cola, like Coca-Cola, and it's a pH of 3. So between 7 and 3, we have 4 pH units. So how many times more acidic is cola than distilled water? That's the question. How many times is cola more acidic than distilled water? So a lot of people that don't understand pH, they just say, well, it's 4 times, because this is 3 and this is 7, or they may say 2.5 times or something like that, 2 1/3, to make it exactly 7. It doesn't work that way. Remember, each one of these pH units is a power of 10. So we're going from 10 to the negative 7th with a pH of 7 to 10 to the negative 3. That's a 10 to the 4th difference. So cola is 10,000 times more acidic than distilled water. You say, well, why do I need to know this? Well, if you're drinking a lot of cola or fruit juices, the acid can erode the enamel on your teeth, especially around the gum lines. Same thing with coffee. It's only 10 to the 2nd time greater, so 100 times greater in acidity than distilled water. But around your tooth, so here's your tooth here, and here's your gum. So around here is where you'll start seeing erosion around teeth. So notice older people who drink a lot of acidic drinks, you'll start seeing erosion here. So to counteract that, you should always drink some water after you drink fruit juices or colas, to try to reduce the acidity around the gum line. So again, when we get to the end here, at the bottom of the pH, so here we have a highly concentrated hydroxide ion concentration of 10 to the 0 power. There shouldn't be a negative there, it's just 10 to the 0. And so that makes the hydrogen ion concentration 10 to the negative 14th. So this is not an acid, this is a strong base, sodium hydroxide. So that's what we got out of the pH scale. The main things is this equation here. You need to be able to use it. You need to be able to use the pH equation, that pH equals negative log of the hydrogen ion concentration. That hydrogen ion concentration has to be in molarity units, moles per liter. That's what the brackets represent, moles per liter. And then the reverse of that is if I want to know what the hydrogen ion concentration is, or the inverse, that would be 10 raised to the negative pH. So that's just a few of the equations you need in order to do that section of this chapter. Next slide pretty much just shows you what those concentrations and pHs are. I'm just trying to show you the relationship between, again, log of 1 is 0. So all these log of 1 is 0. So now we just focus on the exponent. And remember, that's what a log is. A log is the inverse of the exponent. So if this is log of 10 raised to the first power, this is the inverse of that. We get the number 1 for our answer. So that's what you see right here. This is 0. 10 raised to the negative 1 power is negative 1, but pH is negative log, so that correction factor, a negative, and I should have put a negative there if I want to do it that way. That's how we get a positive 1 here. So that's why pH is equal to the negative log of the hydrogen ion concentration. Okay. Did I do that on the last slide correctly? Let's just make sure. Yeah, it's negative log. Okay. So what's the importance of pH? pH control, we see it a lot. If I see a lot of people right now, they're adding fertilizer to their lawn. Well, if that fertilizer has a lot of ammonium ion in it, that's an acidic ion. It's going to make the pH decrease, become less than 7. And there's a certain pH that grass grows at, and it's not something like pH 4. So same thing with any kind of agriculture. Crops depend on a certain pH. Physiology, the same thing. A pH of a shift of 1 pH unit is fatal. This is where it gets to be serious in that, let's say you're in a car accident and your chest hits the steering wheel and that causes some bones to break and you can't get a good breath in. Well, you generally start going into acidosis, where the CO2 builds up in the body and starts making your blood acidic, and that starts doing organ damage. So we have a way of buffering that we'll talk about in this chapter. But a shift of 1 pH unit is fatal, and so it's important that we regulate our pH. Acid rain, we've talked about this a lot, and that acid rain can cause lakes to become fairly acidic. Once they become acidic, you'll start to see changes in the biology. Municipal services, we have to treat the pH of sewage. When this gets out of whack, then bacteria gets out of whack and it gets to be a real problem. And the same thing with industry. Industry has to regulate what comes off of their property. They have to make sure it's the proper pH before they send it to a treatment plant. The next slide is what kind of reactions can we expect with acid-base, and that's going to be acid-base neutralization. So a neutralization reaction is where we take an acid. How do you know it's an acid? Because it's got a terminal hydrogen here. And we see that what happens here is this hydrogen is donated to this to form water. All right, so we know that that's an acid. And then this is a base. It's got the hydroxide ion. Arrhenius said anything that has the hydroxide ion is a base. And so the other substance that forms is a salt. The sodium ion from the base, the chloride ion from the acid that forms, and so we form sodium chloride, which is a salt. A salt just means an ionic compound, and so that is called a neutralization reaction. We had the properties of an acid: sour to taste, base, bitter to taste. Over here we have salt and water. So we talked previously about how to do the molecular equation. That's what this is. It makes it easy to balance. We talked about the ionic equation. That's what's actually present. So when you put hydrochloric acid in water, 100% of it is ionized into hydrogen ions and chloride ions. And sodium hydroxide 100% dissociates into sodium ions and hydroxide ions. And then we do a double replacement where the hydrogen goes with the hydroxide, and the sodium ion goes with the chloride ion. And sodium chloride is water soluble according to the solubility rules. That's why you need to know those that were previously mentioned in this chapter. But water is formed. It's a liquid, and so this is not a precipitation reaction. This is a neutralization reaction. It's an acid-base reaction. We don't see a solid on the product side, so it's not a precipitation reaction. If I remove the spectator ions, those are the ions that do not change from the reactant side to the product side. What I have left is this equation, and this is usually the net ionic equation for a strong acid reacting with a strong base. So make sure you know that. You are going to have on the exam coming up molecular equations, ionic equations, and net ionic equations, not just for precipitation reactions, but also possible for acid-base and oxidation reduction reactions. All right, so there we have it, neutralization. So what's neat about neutralization reactions is that we can use this to determine maybe the amount of unknown acid or base in a solution. And that technique of determining the unknown amount is called a titration. Titration involves a measured amount of a standard solution, which you know the concentration, to neutralize a second unknown solution. So your standard solution is the solution that you know the concentration of it. You've made it in the lab, you've calibrated it, you know what it is. And then you have the unknown. So if you are taking the lab, you may do an acid-base titration. And so you'll have an instrument called the burette. It's a long glass cylinder, and it's calibrated with milliliters on this that you can't see here, but they're little calibrations of milliliters along the glass tubing. And so you put in a given amount of standardized solution, which you know you know what the concentration of it is. So let's say let's say the base is in here. Let's say the acid is in here, and the base is in here. All right. So you will let out the base until all of this is consumed, all the hydrogen ion and the acid is consumed. So you'll know exactly how many milliliters of solution you dispensed, and you will know the concentration of this solution, your standard solution. And from that, if you know the reaction, the chemical reaction between this solution and this solution, you can determine then what the concentration of the hydrogen ion was in the solution. You say, how do I know that? Well, once you add enough hydroxide ion that this is all consumed, that next little drop of base here would change this to a pink. So this was clear to begin with, and then once it changes to a light pink, you know you've consumed all the hydrogen ion that was in your unknown solution. So that's called a titration. So let's look at an example of that. So this is what it looks like in real life. There's a burette and an Erlenmeyer flask. We use an Erlenmeyer flask because it's conical and you can swirl it around. So here we have a base up here in the burette. We have an acid here, and you go, how do you know that? Well, acids in presence of an indicator, like phenolphthalein, are colorless. But once all the acid is used up and a drop of hydroxide ion touches or interacts with the indicator, it changes to pink. So that's when I know to stop the valve on the burette here. Let's see if I can use a different color ink here. That one just not showing up real well. All right, so that burette there, yep, and that's the valve. So it's really neat. I enjoy titrations. It is a technique. It takes time to learn, but once you learn it, it is a valuable technique in determining an unknown amount of acid or base in in this solution here, and it's a what we call a wet chemistry method. It is one of the more enjoyable methods that I like in chemistry lab. So here's how it works. So you add indicator until you've added you add base until you just add enough base for all of the hydronium or hydrogen ion to be consumed in the unknown acid that's present in the Erlenmeyer flask, which looks like that on the previous page. That's called the equivalence point, all right? I want you to know that. The equivalence point is when you've added just enough sodium hydroxide or the hydroxide ion to consume all the hydronium ion that's in your unknown acid solution. The end point is when you see the color change. So you say, are those the same thing? No. The end point will change color through a certain pH range. And you want to choose an indicator that coincides with the equivalence point, but that's sometimes hard to do. It's hard to get one that's just perfect. But for acid base, a strong acid base, we generally use phenolphthalein, and it'll change from colorless in an acidic solution to pink in a basic solution during this equivalence point. So here's how it works. You put in 25 milliliters of acid into this Erlenmeyer flask. You add a couple of drops of indicator, and this is clear, colorless, because it's an acid. Yeah. Here's my burette. Here's my valve. All right. I fill up the burette with sodium hydroxide, and I get an initial reading of how much sodium hydroxide is in the burette. I open up the valve, swirl it around until, and I know also the concentration of this. Let's make sure we do that. Concentration of this is 0.1000 molar. And open up the valve, and I notice that this thing flows down, and then this turns the lightest of pink, I stop, and I get a reading. I take my final reading here minus my initial reading here, and I find out that I added 35.00 milliliters of sodium hydroxide. So I know how much sodium hydroxide I added. I know what the concentration of the sodium hydroxide is. I know the volume of the hydrochloric acid. And I know this reaction, is sodium hydroxide reacts with hydrochloric acid, and that forms salt, which we're not interested in, and the other substance is water. So I know that's the reaction, it's balanced, it's 1 to 1. So for every 1 mole of hydrochloric acid consumed, 1 mole of sodium hydroxide is consumed. So now I can calculate, using these numbers here, how much the concentration of the base, sodium hydroxide, how much I dispensed. I can determine, and knowing this is 1 to 1, I can determine the moles of hydrochloric acid in this beaker, this Erlenmeyer flask, and I know the volume of it, which I can convert to liters, and that'll give me the molarity of my unknown acid solution. So that's what's cool about doing titrations. All right, so here's what the calculation looks like. So calculation, we took our 35 milliliters of sodium hydroxide dispensed. We convert the milliliters to liters. Now, for me, I would have said 10 to the negative 3 here, and I would have just said 1 milliliter here, because milli means 10 to the negative 3. Either way you want to do it, still comes up to the same answer. And then our concentration of the sodium hydroxide is 0.100 moles per liter. That's the molarity. And I've set this up right because the milliliters cancel out, the liters cancel out, and I'm left with moles of sodium hydroxide. So this is how many moles of sodium hydroxide I dispensed out of the burette. I know that the relationship in the balanced chemical reaction is for every 1 mole of sodium hydroxide consumed, 1 mole of HCl is consumed. So that's my mole to mole ratio that we learned how to do when we did stoichiometry problems. So we transform the moles of sodium hydroxide into moles of hydrochloric acid. If I take the moles of hydrochloric acid and I divide it by the liters of hydrochloric acid that was in the Erlenmeyer flask, that's what this is doing. It's converting the milliliters into liters. Because remember, molarity is equal to moles divided by liters. So we had to convert the milliliters into liters. If I divide that, 3.5 times 10 to the negative third, by this comes out to be 0.025 liters. I get a concentration of the hydrochloric acid to be 0.1400 molar. So that's what's cool about titrations, is now I know what the concentration of my unknown acid was in the beaker based off the standard solution of sodium hydroxide that I know its concentration and how much sodium hydroxide I dispensed in the reaction. All right, this next slide is about some acids are not monoprotic, some acids are polyprotic. So polyprotic means more than one acidic hydrogen. So when we look at something like sulfuric acid, we see 2 terminal hydrogens. And so notice when instead of doing HCl and sodium hydroxide, which is 1 to 1, when we did that reaction, we said HCl plus sodium hydroxide, so hydrochloric acid plus sodium hydroxide, yields water plus salt, and it was a 1 to 1 relationship here, 1 mole, 1 mole. But because sulfuric acid is diprotic or polyprotic, it takes twice as much sodium hydroxide to neutralize all of the acidic hydrogens. So just keep that in mind, is that when you're looking at an acid, you need to determine, is it monoprotic, like hydrochloric acid, hydrofluoric, hydrobromic, hydroodic, or is it diprotic like sulfuric acid? Because it's going to take twice as much sodium hydroxide to neutralize that reaction versus hydrochloric acid. And you can see that from the balanced chemical equation. So what happens in a diprotic reaction is that we have sulfuric acid. It can react with water, donates a hydrogen ion to the water becomes the hydronium ion, and then what's left over is hydrogen sulfate. And so that's another acidic hydrogen here, and so this has the ability to donate another hydrogen ion to the water and form more hydronium ion. Now there's a typo right here. This should be a double-headed arrow. This reaction, this is a weak acid. This is a strong acid here, but this is a weak acid. This is not one of the 7 strong acids that you need to memorize. So this reaction does not go 100% to completion. It may only go about 20% to completion. This reaction up here, you see the arrow only goes one way. That one goes 100% to completion. So weak acids are reversible. They can go this way, they can go this way, and eventually there's an equilibrium between what's on the reactant side and what's on the product side. Think of it like a seesaw. It's nice and balanced. Whereas this one, 100% of it goes to product. It only goes one way. So every bit of this is going to be converted to that. Same thing can happen with bases. So with bases, we have something like barium hydroxide. So barium hydroxide, you have 1 mole of it, but there are 2 hydroxides. So the first thing that can happen is 1 hydroxide can come off. This is called dissociation. And then the second hydroxide can come off. So for every 1 barium hydroxide, you get 2 moles of hydroxide ion. All right, this section is really important, especially allied health. This is called buffer solutions. So this buffer solution, we have a buffer solution in our bloodstream so that when we drink something acidic like a Coke, 10,000 times more acidic than water, if that went right into our bloodstream, it would kill us. So we would have a pH change, a pH 4, a 4, a change in pH of 4, right, which is 10,000 times. So we have to have a way to absorb acid or base without the pH changing appreciably. Same thing if you have fish you have an aquarium. You got to keep the pH of the water at a certain level in your aquarium, otherwise the fish die. And if it's not optimum, the fish do not thrive. So you're always measuring pH of the water, and as the fish excrete waste, it does change the pH of the water. That's why you got to change the tank. Where else you'd see this is a pool, swimming pool. If the pH of the water is not correct in a swimming pool, when people jump into the pool, it can cause their hair color to change. It can cause their hair to fall off. And so when it's very basic, again, it'll cause people's hair to become detached from the body. There'll be a bunch of hair in the drain. So we put buffers in the pool, so it maintains a fairly consistent pH regardless of who's jumping in or how many people's jumping in or whatever. So that's what it does. So let's look at this. And so buffer is a solution that resists large changes in both in pH when either an acid or base is added. So that's the key. It's not a buffer if it can just resist acid being added. It's not a buffer if just adding base it can resist the pH change with a base added. A buffer has to be able to resist both additions of acid or base. It has to maintain that pH even once we add an acid or a base. If it just maintains the pH after adding an acid or a base, then it's, if it can only handle one of them, acid or base, and that's it, it's not a buffer. So what are the key components of a buffer? A buffer it's going to be a weak acid and its conjugate base. We've talked about that previously. A conjugate base is when we remove a hydrogen ion from an acid. What's left over, it's called the conjugate base. It can also be a weak base and its conjugate acid. So the example that they show in this slide is the acetic acid buffer. This is a common one. So acetic acid is this substance. If we remove this hydrogen ion, which is the acidic hydrogen, we have this substance left over with a negative charge. This is called the conjugate base. So this is the acid, that's its conjugate base. So you can see, again, this should be a double-headed arrow here. There's something wrong with the PowerPoint there. But the hydrogen ion leaves the acetic acid, it goes to the water, and it forms a hydronium ion. So now we have an acidic solution. What's left over after the hydrogen ion ionizes is the acetate ion. So that's the correct term, ionizes, because we don't have any ions over here. We end up with ions. Because it's double-headed arrow here, that means this reaction does not go 100% to completion. This is not one of your 7 strong acids. Acetic acid is a weak acid, which wants to stay mostly in the molecular form, like this, and not the ionic form that you see here. So, in this solution, we have a weak acid, which wants to stay in this form, and we have the conjugate base of a weak acid, which could accept hydrogen ions and become the weak acid. And this, so think of it like a seesaw. On this side of the seesaw, you have the weak acid, And on this side of the seesaw, you have its conjugate base. So if I add hydrogen ion, the seesaw gets out of tilt like this because you've added hydrogen on, and the reaction has to shift in such a way as to relieve that stress to get back to equilibrium. If I add hydroxide ion, the hydroxide ion is going to cause this side to be like this, and so then the hydroxide is going to react with that, because the hydroxide ion is going to react with the hydrogen ion, and we're going to see a shift this way to get back to equilibrium. Okay. That's one way to discuss it. There is another way you could discuss it. You could say the hydrogen ion reacts with the hydroxide ion reacts with this and forms water. Because we see a decrease in this, the reaction has to shift in such a way as to make up that loss. And if I add hydrogen ion, it reacts with this as well. Yeah, I still like this method better. Let's just forget about that thought like that. Let's think about it just like we said. If we add hydroxide, it's going to react with the acid. If we add the hydrogen ion, it's going to react with the conjugate base. I think that's a better way to go. But this is called Le Chatelier's principle. You can, if you don't know Le Chatelier's principle, you can read chapter 7 about Le Chatelier's principle. We just covered it. But make sure you understand what's going on here. That a buffer has the ability to absorb both excess acid and excess base. All right, so this book does take it like I was going to say. If you add hydroxide ion, it reacts with this, which makes sense. And that causes this side to not have enough hydronium ion. And so the reaction has to shift in such a way as to relieve that stress. All right. You've consumed this. This goes down in concentration, which makes this side lighter now. It doesn't have this substance present that it did have at equilibrium. And so the reaction has to shift to the right, to the products, to get back to equilibrium. All right, let's talk about the next one. So, if you add acid, that'll increase this overall. All right, so we are at equilibrium. Everything is equal. We add more hydronium ion, which is the acid, which causes this to get out of whack like so. And the reaction will shift in such a way as to relieve that stress. So what happens is the excess hydronium ion reacts with this and forms more of this to get back to equilibrium. Okay, so it was nice in equilibrium. It was nice and balanced. We added additional acid. It causes this to be too much. This then has to react with this, which then forms more of the unionized acid to get back to equilibrium. So Le Chatelier's principle, the easiest way to remember it is a body is in equilibrium when we apply a stress like excess hydronium ion. This is the way it affects the system. The system will shift in such a way as to relieve the stress. All right, let's go back to the last one just to emphasize that same thing. So let's go back to the last slide. So in this case, we take the hydroxide ion and it removes this concentration decreases. So we were stress free here. We've added hydroxide, which consumes the hydronium ion, which makes it lighter on this end. So the reaction has to shift to the right to the products to relieve that stress to get back to equilibrium. So that's how a buffer works. It has to have the ability to absorb both acid and base, and it is a weak acid with its conjugate base, like this one is, or it's a weak base with its conjugate acid. All right. So the summary is that the addition of acid or base can be absorbed by the buffer. Now, if you add so much acid that all of this is consumed, or you add so much base that all of this is consumed, and that means all of this is consumed, then the buffer is broken, it no longer works. So you've exceeded the buffering capacity. You can't just keep adding acid or base. Eventually, one of your substances is going to be consumed, either this substance or this one. But once they're consumed, the buffer stops working. So then the next thing I hear students say is, well, I'm going to add a lot of this, and I'm going to add a lot of this, and then the buffer will work for a longer period of time. Well, it doesn't work that way. If you add too much buffer, if you add too much of these two solutions, first of all, you're limited by the saturation point or solubility. But it could be that it's so dense, or it's so salty, if you want to think of it that way, that it pulls the water out of the fish and dehydrates the fish, and it dies, not because of the pH, but because the solution, the water is too salty. It's not like a fresh, it's not like fresh water. So that can be a problem too. So that's what this slide says. Buffering capacity. Buffering capacity, how much can you add before you break the buffer? And so once you break that, it's no longer a buffer. All right, next one. So to determine the buffering capacity of the solution, what you have to do is you take your balanced chemical equation, you put the concentrations of the products in the numerator, you put the concentration of the acid in the denominator. Water does not change appreciably in concentration during the course of the reaction, so it's actually integrated into the this constant called the acidity constant, Ka. And so we don't see water over here on the right hand side because it's a constant and it's part of this K here. So if you want to solve for pH, we know pH is negative log of the hydrogen ion concentration, or hydronium ion. So we need to manipulate this equation to solve for the hydronium ion. Okay, so let's do that. So when we move the equation around, this is what it looks like. Hydronium ion all by itself. And on the other side we have Ka, and we have the weak acid and its conjugate base. Alright, so that shows you the steps how we manipulated it from the previous slide. Alright, so in general, what you'll see here is that for any weak acid, the hydronium ion concentration is equal to its Ka acidity constant, acid over its conjugate base. right, so that's just the general form of the equation. So what we do is we take the negative log of, yeah, I'm getting ahead of myself here. So let's say they want us to determine what the pH of a buffer is, in which the concentration, the Ka is 1.75 times 10 to the negative fifth. The acid concentration is 2.0 times 10 to the negative 2, and the conjugate base concentration is 2.0 times 10 to the negative 2. Maximum buffer capacity occurs when these two concentrations are equal. All right, so keep that in mind. So that becomes 1 there, and we have the hydronium ion concentration is equal to 1.75 times 10 to the negative fifth. If I take the negative log of that, I will get a pH of 4.76. So for acetic acid, that's its Ka. That's the Ka for acetic acid, the acid acidity constant. The maximum buffering capacity is at 4.76. So if I want to have maximum buffering capacity, that solution is best at 4.76. Now, can I manipulate it a little bit? Yes, you can. If you manipulate it a lot, you'll probably use a different acid other than acetic acid. So a lot of students say, is there an easier way to do this? Yes, there is. So in comes Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is when we take the negative log of everything here. So we get the negative log of the Ka, we get the negative log of the hydronium ion concentration, we get the negative log of the conjugate base over the acid. They've made a mistake here. This should be negative log of the acid over the conjugate base. All right, they made a mistake. Let's make sure that's correct. I believe they made a mistake there. Let's make sure, though. Yeah. So you see here, it's acid over the conjugate base, acid over the conjugate base. So they've made a mistake. It's okay. Now, so when we look at this slide, we know that P stands for negative log. And so instead of saying negative log, to make it more compact, we just say pKa, and negative log of the hydronium is pH, and then we have the negative log of the conjugate base over the acid. All right. There's a mistake here. This should be a plus sign. If you're going to say conjugate base over the acid, this has to be a plus sign here. That's the problem. Let's see if they correct that at some point. Nope. Well, they don't correct it in the next slide, but that is what happens. If you want to change the sign on the equation, then what you have to do is you have to change, to make this a positive here, you had to flip this. And when you flip that, that makes it the conjugate base over the acid. So when you do that, that changes that sign to a positive. So you are going to see they didn't correct that mistake, and we'll just have to go with it. But it is a plus here. You're adding. All right. So the next thing is how this pH system works. So again, blood's really important. Those of you taking an allied health field, remember this is a double-headed arrow here. So we have carbonic acid, which is in the bloodstream, and then we have the hydrogen carbonate ion. So this is a weak acid. There's the conjugate base of the weak acid. And so this allows our blood to, if we add excess hydroxide ion, it's going to react with this hydronium. It's going to make this side get lighter, so to speak, because there's not as much hydronium ion as there should be as far as number of hydronium ion molecules. So the reaction has to shift to the right to make up for that. If we add excess hydronium ion, excess acid, it's going to react with this. And so once that happens, we will see it get too heavy on this side, and it'll shift to the right to make up for that excess hydronium ion. So again, this is going to happen until we get back to equilibrium, which we are. That's the driving force, trying to get back to an equilibrium. So if you have high CO2 shifts the equilibrium to the right. Blood becomes acidic, and that's called acidosis. A lot of times that happens with people with emphysema and pneumonia. If you have low CO2, like you're hyperventilating, commonly caused by hyperventilation, the blood becomes acidic, which is called alkalosis, and that causes problems too. Again, when we vary the pH, it starts affecting our whole system, our whole body. So again, they said a change of pH of 1 can be fatal. All right, that's where we'll stop at today, and I will pick up on this on oxidation and finish chapter 8 in the next video.